Well, it looks like it's official again, folks. Welcome back. We are on our second to the last class, aside from the final exam that we'll have next Monday. So we're just about there. In fact, we're only one problem away from completing all of the course information. So congratulations on sticking through it. I think statistics is pretty tough. It's a long slog, but it's not that bad once you get to the very end. It's mostly just sticking through it. So after we finish section 15.4, we'll begin reviewing on this document right here. But I just wanted to throw out, if you do have some problems that you would like to see done, whether it's a further problem on this, somewhere on homework or anything whatsoever, don't hesitate to ask. I'll be happy to interject a problem into that document there. Any questions at all, folks, before we get started today? Okay, well, let's begin with 15.4, and then we'll walk directly into the review. So here's where we left off, right on a big example on a hypothesis testing for quantitative data. Jumping into this one, the first thing that we notice is it provided the raw data. So maybe even before you read the problem, if you see this, a whole bunch of data provided, it's not a bad idea to just start by turning on the calculator, import all that data, and we'll get our summary statistics out of that. You can expect to have to do that kind of thing at least once on a real final exam. So this is a pretty good review in and of itself. Step one, hit the stat button, hit enter right away, and clear out your data. So we only need one column of data since we're not doing any kind of regression on this. So I'll type these in going row-wise. This is the quiet part of class while we get our data in. Data entry is extremely tedious, but it is an important science. It's part of statistics in the worst kind of way. Oh, and I just made a mistake. By the way, as far as data entry goes, this is a really great way to accidentally produce an outlier, putting in 79 instead of 7.9. Sometimes that's all outliers are when people go to investigate them in the data. It was just a small error that has to get corrected. Okay, I think I have all the data, 15 values. Let me give the class a few more moments to get it all imported in. Anyone need any additional time? Okay, with all that data in, let me know if your values are different from mine. Hit the stat button, right arrow on the keypad to go to calculate, and then just hit enter a whole bunch of times. It should say L1 here first, just to double check. After hitting enter, here's where we're getting our data. X bar, that's the thing I incorrectly wrote down in the notes a whole bunch of times before we got all those typos tracked down. We use Y bar, but same kind of thing. No harm done if you did say X bar. The Y bar means the mean of the sample that we're just looking at, and it comes out at 6.6. Next, we have a sample standard deviation. It's always good to emphasize this. Be sure to get the one that says SX, not the one right below sigma. So S, or SX if you prefer to write it, is 0.67. Hard to know how much decimal places to round this one to, but because this is to 2 decimal places, the question down below, I'd say this is pretty appropriate. On a real final exam, I would try to be a little bit more precise on indicating what to round to. And if I didn't, then whatever you decide, I'll just go with as well. So if someone rounded this to 0.7, then as long as your work is okay, I'd be happy with that. Oh, well, we've got the statistics in. Any questions about getting those? Okay, well, we got the easy part out of the way, just importing data and crunching out these 2 statistic values. The hard part is digesting all this context so we can write down the parameter, state the null and alternative hypothesis. So here's how the problem starts in earnest. It says, acid rain from the burning of fossil fuels has caused many of the lakes around the world to become acidic. So that's good information. The biology in these lakes often collapses. That's not great, but this is what happens because of the rapid and unfavorable changes in water chemistry. So it's a concerning problem where your entire biology of a lake can just suddenly become dead, no fish, no anything like that. It's happened to some lakes in California, like Lake Mead, for example. They tell us here a lake is classified as non-acidic if it has a pH greater than 6. We don't really know what to do with that information yet, but let's highlight it. And thinking about how the last problem went down, you might suspect that this value 6 might be the hypothesized mean, mu naught. We could be wrong about that, but let's put that down right now just to see, just in case, rather. So next part of the problem says, these researchers, A. Marchetto, A. Lamy, measured the pH of high mountain lakes in the Southern Alps and reported their findings in that paper indicated there. So that's these 15 values that are indicated down below here. And this looks like it's talking about the sample and the population as well. So let's highlight this. We'll definitely need that information again. So it says the pH levels obtained by the researchers for a random sample of the 15 lakes are given below. So we have a nice random sample. Next, it asks, at the 5% significance level, from this portion right here, it's a good idea to write down alpha equals 0.05. That's going to be what we've compared the p-value against. So let's get back to that question. At the 5% significance level, does the data provide significant evidence to conclude that, on average, high mountain lakes in the Southern Alps have a pH different from 6.35? So that's kind of a surprise. They talked about something at pH of 6, but the actual value we're going to be testing is 6.35 after looking into it further. So let's X that out. It was good information. I mean, that's going to look weird on the notes. I'll delete it rather. Let's go over here now and indicate this is the real value to be tested, 6.35. We'd have to ask the biologist why specifically 3.65. It's probably a very important reason for that. So far, this is everything we know about the problem. And we're just going to start, as we always do with these, describe the unknown parameter using the context. So we can begin by saying mu equals, our data is quantitative, it has units, so it's going to be the true average. Like before, you could say the population mean, population average. I'll go with true average on this one, just to mix it up. So it's the true average of all. Here's where it gets a little bit trickier. Or hang on. This sentence would look a little bit weird if we just leave it off like that. Let's say true average this way. True average of the pH. So for this part right here, we're mentioning what the data is. In other words, the data that we're looking at here are all pH values from measurements taken from those lakes. So the next portion, we'll say for all. This is the part I skipped to, and the sentence could be okay if we put the population here, but I feel like it just would read weird. So in this portion, we're indicating the population. And this one, it's kind of tricky. We can't say all lakes, for example, because that's really not the spirit of this study. This is about specifically high mountain lakes. And the way we could double check that that ought to be the right population is we go back to the data. You know, one thing I forgot to write down is we have a sample size of 15 coming from right here. So as a sample size of 15, these researchers grabbed 15 lakes from the high mountain lakes in the Southern Alps. And so that means we're talking about a population of all high mountain lakes in the Southern Alps. So all high mountain lakes in the Southern Alps. I'm going to have to move that note there. Okay, so we've got our population in. The parameter is saying an average of a quantity specifically, the pH, and for the specific population as well. So that's what gets us the full parameter. Let me just put a quick note here, since we're used to seeing it at this point. This is the population. So if you go back to on the old notes, you'll notice every parameter we wrote down, whether it was mu or p, it had this kind of flavor. Either we put in the data mentioning the units, or we just mentioned what a success is, and then we mentioned the population as well. Any questions at all with getting the parameter down? Okay, going forward, we're ready for the null and alternative. Let's say here we will test H naught, that mu is equal to a specific value. It comes from right here where we wrote down mu naught, so 6.35. So we test that against HA, the alternative hypothesis. This is mu, something goes in the middle. There's always a struggle to find out exactly what this alternative looks like, but 6.35 would go here again. So anyone see what should go in the middle? What kind of a test it is, in other words? Right tail, left tail, or two tail? It turns out this one is not a right tail test. There's a pretty good hint on this one, though. When you're thinking of what should go here, you're thinking about the alternative hypothesis. And not always, but in a lot of these problems, if you're thinking about the alternative hypothesis, you're looking at where the question is in the problem, because that's the research question we're trying to answer. So it happened on this sentence here, and somewhere in this sentence, it has to be dug out. There's an indication of the type of test. Anyone see the key word inside that sentence? Good call, it's the word different. That word alone says two-tailed test. We're going to use a not equals in our alternative hypothesis. If it said more than, we would have been a greater than here. If it said less than, we would have put a less than here instead. Does that make sense with that keyword there? Exactly, yeah. Exactly, yeah. It's kind of a weird problem because this part indicates acidity greater than 6, so we think that should be what they're testing. But no, they have no idea what's happening in these high mountain lakes. Maybe they're not are acidic. Maybe it could be a less than here or a greater than. They're not really sure, so they're just checking, is it different from 6.35, going for the two-tailed test now. That's tricky enough to always want to try to highlight that keyword once you spot it. There it is. From there, we have a two-tailed test, which means down here, it'll be a not equals. So we have one big sentence. We're testing H naught against HA at, last thing we say is the significance level, alpha equals 0.05. So that's our one big sentence we're going to take a look at. We have the parameter up above. And the rest of this is basically take a look at your formula sheet to see how it all connects together and plug in the information. That's pretty much the experience in statistics. So let's scroll down a little bit more and start cranking these out. First, any questions whatsoever with the parameter or the hypotheses? Okay, so a lot of these things are also keywords. Whenever you see degrees of freedom, think symbol DF. That gives us the formula n-1. Go up to the sample size, written down over here, kind of late actually at 15. And it'll just be a 15 minus 1. Oh, sorry, missed your response there, Tiffany. I'm getting really bad at checking those chats, but you're correct. That was a two-tailed test. So in this problem, we'll have 15 minus 1 for 14 degrees of freedom. Next up is our standard error. We usually use green for that in the color coding. This one's tricky because if you're looking in your notes for standard error, imagining this is a real final exam problem, you'll notice there's two formulas. But if you have a y bar going on and you wrote down a mu, then this one is going to be standard error for the sample mean y bar. So the formula then becomes S divided by the square root of our sample size n. So quantitative data gives us the nice standard error formula. If it's categorical, we have to work a little bit harder. So let's go over here, plug in 0.67 for S, divide by square root of n, which we indicate up here. So divide by square root 15. So back to the calculator. This is a 0.67 divide by, hit second key, power 2 button for your square root, plug in 15. So we've got, for 4 decimal places, a standard error of 0.17, rounding with carry, 30. Any questions so far, folks, on our standard error portion? Yeah. Yeah, that's actually pretty tricky. For the degrees of freedom, it's one less, but when we use this formula, we use the full sample size. Yeah, that's a common mistake I've personally made myself. And the calculator, if you wrote down 15 or 14 once, it's tempting to write it down again. So that's a really important mistake to watch out for. Well, let's try out the test statistic next. This is nothing but a z-score. So when you see the test statistic, you're calculating t, because it's quantitative data, and we're using the t distribution for a p-value. Formula then goes y bar minus mu naught. The naught meaning we're getting the value from the null hypothesis, divide by standard error, y bar. So all we've done here is just copy down the formula. That's good for partial credit just on its own, but now we have to substitute in that information. Let me see if I can zoom out just a touch. So for y bar, let's plug in 6.6 from way up here. Subtract from the null hypothesis the value 6.35. And finally, divide from the prior step on the standard error, 0.1730. That rounding just looks a little odd to me. Let me double check it. Yeah, that is rounding with a carry, 1730. So that has to go into the calculator. We mentioned this a lot in class, but it actually makes a big difference on the average score on the final exam. Don't forget to write this down on paper before putting in your calculator, just in case you make a simple mistake. You could be really surprised that even if you've done this kind of stuff for years, it's extremely easy to make a mistake on this. But if I see this is correct on paper, that's where essentially all the partial credit will be awarded. So 6.6 minus 6.35 divide by 0.1730 gives us a test statistic value of 1.4451 standard deviations. That's not a lot. So it looks like we're probably not going to reject the null hypothesis on this one, but we still have to compute the p-value on the next step. So this equals 1.4451. And just a reminder of what we really calculated, what this says, just to help with the logic of hypothesis testing, is our data, when we say our data, we're thinking y bar, is 1.4451 standard deviations away from the claim in H naught, the claim that the true mean is 6.35. Again, that's not too many standard deviations. That could happen by random selection quite often. And we'll see just how often that could happen by calculating the p-value next. Any questions first with our test statistic? Okay, well, this one is a two-tailed test, so we need to be pretty careful when we go to write out this p-value. In fact, let's begin just by saying two-tailed test, just as a reminder of how this one will go. So the two-tailed test, even though you don't have to sketch a diagram, let's do it once more for the sake of the notes. It's hard to draw a horizontal line sometimes. So here's my shoddy T distribution graph. Does not have to be perfect whatsoever. This is the T, come up here, 14 distribution. We're grabbing the degrees of freedom from part C to describe it. Centered at 0, right at its main peak. And we're interested in this value here, 1.4451. So we have T goes into about this location. It causes a segment to come up here, and this area is not the p-value, but once we double it, we do get that p-value area. At least with what we have so far in this diagram, we have a setup for the calculator. This is what it would look like. Input 1, lower, is the 1.4451, the test statistic. Because we're shading the area to go to the right forever, input 2, upper, is 10 power 99. And input 3 is just the degrees of freedom, 14. So we go to this portion of the calculator, TCDF. And finally, we can write that the p-value equals, this next step I'm writing down is really just so that I don't forget to do something very important. In the two-tailed test, the easy mistake to make here is forgetting to double your p-value. But if you put times 2 right here, that's a pretty good protection. So now we're back in the calculator, hit second and bars to pull up your distributions. We're going down to option 6, TCDF. If you have the TID3, it might not be option 6 because the TID3 is missing inverse T. It's kind of curious. So go to TCDF. Lower is 1.4451. Upper is the 10 power 99. We said degrees of freedom is 14. And so come down here, hit enter once, and that's half of our p-value, 0.0852. Now the calculator, if you just go times 2 and write that down, that's completely fine. But I'm also doing it this way on the notes just as a big reminder, not to forget to double. So 0.0852 goes here. And so now our p-value becomes, and the calculator's hit times 2. Should look about like that. And this is finally our p-value, 0.1704. So our p-value is large. It's literally twice as large if it was a left-tailed test or a right-tailed test. But this is the test that they indicated in the research hypothesis, so we have to stick to it. Looking up above, our significance level is at 0.05, but it wouldn't have made any difference, really. The largest people typically go is 0.10, and this is exceeding already one of the largest significance levels people would typically put down for this kind of problem. So maybe the last thing we want to write down here is the p-value at 0.1704 is bigger than 0.05, which was our significance level alpha. And so this means we fail to reject H naught, which means not only was this a tricky test being a two-tailed one, but the conclusion is extra tricky as well when you fail to reject H naught. So that's going to be our last part. And hey, this means this is the last part of the entire course. After this is just a review. So congratulations, we just need one more practical interpretation. Any questions first whatsoever with the p-value? Okay, let's come up here. For our conclusion, we're going to need the parameter and our hypotheses. Probably doesn't need to be that big. Let's move that down. So observing the p-value again is larger than alpha, we would say the following. This study does not provide significant statistical evidence to support the claim that. Now, after we write out all of that, this is pretty much the generic statement when we fail to reject null hypothesis. We come down here and just say what the claim was that we didn't find evidence for. We have to avoid saying we found evidence that this is true, however. That's the big thing that we always avoid in hypothesis testing. So we come over here, write out what we said mu was, the true average of pH values for all high mountain lakes in the Southern Alps Okay, so I just wrote out what the parameter was, is different from 6.35 is how we would end the statement. Is different from .35. So in other words, we did not find any evidence that these high mountain lakes in the Southern Alps are typical or atypical from our expectation of 6.35. Didn't prove that they have a pH value of 6.35. Our sample size was small. It probably is different, but with a small sample size of just 15, we couldn't detect it with our data. So that's why we said it didn't provide this significant evidence. We're not trying to make a claim that we know it's true or we know it's false. We are just saying we don't have evidence to support either direction now. Kind of a sad conclusion in a certain sense, but it's an honest one. Any last questions or comments, folks, with our conclusion here? Okay, well, that was the last problem in the whole course. So congratulations on getting through all these. I don't know how many problems we solved, but by the end of the 15-week semester, it usually feels like a lot. So let's save this up. We'll get them uploaded as before. And now we're at the review for the final exam portion of the semester. So that takes us to this document right here called the final exam review. And all this is a selection of problems. Most of them, I hope all of them, but I think some of them could be similar. Most of the problems I put there are different from the ones that you see right here. So they're fresh extra questions to take a look at. I'll leave all of these here for your personal study, but if there's any problems from that set or anywhere else you would like to take a look at, let me know at any time as we go through these problems right here. So let's open up that document, final exam review. Get my windows going. There we go. And maybe before we start the final exam review, let's take a look at the Moodle course for just a moment. Take a bit of a breather. I made a couple change of hearts on this final exam. I put here on the write-up for the final exam version 1. If you took a look at this earlier, you might have noticed there was a write-up saying, I intend to ask a question on hypothesis testing for means, proportions, and a confidence interval questions for both means and proportions. So that would be 4 statistical inference questions. But then I had a change of heart when I wrote the final exam. That's a pretty long exam if we ask all 4 of those questions. So I changed it up a little bit. Let me see where I indicated that. On the final exam, there will be exactly 1 confidence interval problem. So it'll either be for proportions or it will be for a mean. And I'll choose it by actual random selection. So there'll be some randomization on the exam. Then there'll be 1 hypothesis testing question as well. I said I'm going to choose this one by random selection, but the thing I didn't really write here that I want to say is here, If I choose a mean for the confidence interval, I'll do a proportion for the hypothesis test, and vice versa. If I did a proportion for the confidence interval here, that would mean we ought to do a mean for the hypothesis test down there to get a good amount of representative problems. So only expect 2 statistical inference questions and you'd be on the right track. Any questions about that so far? Okay. Then on the top of this document, on the final exam review, all of the questions start out as inferential statistical methods. So these are all confidence intervals, hypothesis tests from example 1, 2, 3, and 3 to 5, apparently. So that's interesting counting. Down below, this is all the other problems in the course. Things like box plots, normal distributions, outliers, z-scores, that kind of stuff, regression analysis. So I want to leave it kind of up to the class. We could either start on the other review problems and go our way down, or we could start on inferential statistics, work our way down, or we could just kind of do one and the other. Maybe example 1 here, change it up to something down here on the other problems. Really, it's kind of up to us. Anyone have a strong opinion one way or another? Start right here on the other problems? I honestly think that's a good idea because if we started at the very top, these are the problems we were just looking at, right? So it wouldn't feel as fresh for a review. So let's go down. Thanks for making an indication on that. And start right down here. So we'll work our way down, solving as much of these as we can before the day is out today. And we'll come back to this location on Thursday's class as well. So this starts off by saying, as part of a marketing team at an internet music site, you need to understand the demographics of your customers. We have a simple random sample of 20 customers selected. Not too sure if we need this, but just in case formulas come up, we might need that. We are told next, one of the variables of interest is the age of the music site users. So we have an internet site, a marketing firm is working on this. They took 20 customers. This is a random sample. And this is the age of all those customers at that site. So some of them probably shouldn't have been on there. I don't know where this person got their credit card. And there's some older people on there, usually normal kind of data you'd see here. It says describe the population of interest. So we might start by saying the population is all. Well, this is kind of tricky. It's not these numbers. These are just the ages. That's the data. It's not necessarily describing the population itself. Anyone see a good way to describe the population? Exactly. The marketing team only cares about people who are on that music site. Good call. They don't care about anywhere else, whether it's Napster or whatever it might be. So all users of this internet music site, that's really stated in a weird way, this music site. So we've got our population down. This one's tricky because we've been doing parameters for so long. It's tempting to say mu equals the population mean of the ages for all users at this internet site, but it just wanted the population, no parameter. Next, we want a 5-number summary. That could take some work on its own if you did it by hand. So this is where you want to turn on the calculator, hit the stat button, enter right away, delete your old data, and just start putting these in. So 20 values, 20, 32, 34. Sorry, I shouldn't say that. I think I throw people off. Okay, I think I've got the data imported. Anyone need any additional time? Okay, So next thing, oh, sorry. Just give a few more moments. Oh, no worries at all. No worries. That was pretty quick. So next moment, our next step is hit stat key, right arrow to calculate, enter, making sure L1 is there. I mean, usually we don't do anything on this window, so nothing has to change. Just hit enter a bunch of times. And this is the confusing part of the calculator. If this happened to you on a final exam situation, this would be a question I could help out with, because it's easy to forget when you're a little bit stressed out in a final exam what that down arrow is saying. You have to go down, and this is where your 5-number summary actually lives. So it goes from minimum to maximum, those values. So the data is contained between min equals 11 years, quartile 1, this is the 25th percentile, is 22 years. Then we have the median, M, that's the 50th percentile at 29 years. Next, we're at quartile 3. Quartile 3 is up to 33 years. And finally, we've got a max. The maximum age was 50 years. So we've got all that in. Next thing we're going to investigate is, are there outliers in the data set? So this is a definite formula that you want to keep in mind for your notes for the final exam, the 1.5 IQR rule of thumb. It's a kind of a nice formula because the name of the formula contains a part of the formula in and of itself. You take 1.5 times the IQR using the rule. But the thing you'd probably want to refresh or put down in your notes is, this is how we use it in full. We calculate a lower bound, and we calculate an upper bound. Anything below this number will be an outlier, and anything above the upper bound will also be an outlier. So let's write down our formulas. Lower bound goes like this. We take the lower quartile, Q1, we subtract 1.5 times interquartile range. For upper bound, almost the same kind of thing, except we take the upper quartile, Q3, add 1.5 IQR times the IQR. So a good way to memorize this is, when it says lower bound, you're subtracting and you're dealing with Q1. And when it says upper bound, you're adding and you're dealing with Q3. So lower to Q1, upper to Q3 with the pluses and minuses, kind of makes it feel logical. Any kind of little mnemonic, that's a weird word, mnemonic? Mnemonic. Any kind of memory trick, let's just say the word instead of that one. Any kind of memory trick you can come up with for memorizing this helps out a fantastic amount. But let's now put in the data. Well, I guess there's one thing we have to do first, right? We need to calculate interquartile range. Let's do it up here, maybe.
Is that Q3 minus Q1?
Exactly, good call. So the upper minus the lower. If you got them subtracted backwards, you would just get a negative number, and that would be your indication you've got the right value. Just take off the negative sign. So let's go here in the calculator. Let me hit just second and quit to get out of there. Quartile 3 was 33 years. Minus quartile 1 at 22 years. Guess I didn't need a calculator for that, but at least we are more accurate. This came out at 11 years. So using the value here for quartile 3 and the value here for quartile 1. Okay, now we're ready to write down values. This one is going to be Q1, 22 years, minus 1.5 times 11. For the one down below, Q3, we're going to plug in 33 years and add to it 1.5 times 11. So we're handling both at once. And now for first one, 22, go minus 1.5 times 11 to get us started. That one is at a value 5.5, but that would be 5.5 years, I would be astounded at 5.5-year-old in an internet music site buying music. So there shouldn't be an outlier below on the lower end, but we should check. You could look through all this data, seeing if anything's below 5.5, or simply look at the minimum. The minimum is at 11 years. That means there's nothing at or below 5.5 years. And so this tells us finally, no outliers on the low end. Now we check the upper end. You can up arrow here twice, paste that down and just change this to a plus in the middle. And at 33, don't forget to change to the upper quartile now. Now it becomes 49.5 years. Yeah, it looks like that one person, the 50-year-old in this data set, would then be an outlier. Good call. So now that we have the 49.5 years, forgot to pluralize that, we can say that this value is the outlier. Let's write down below. There is one outlier at 50 years. So we've got the outlier down. Next thing we're going to do is create a dot plot of all these data up here. Using the x-axis provided below, well, we've got an axis. So I guess we could expect that on a real exam. Oh, didn't mean to make it too big. It's kind of hard to actually get it to format well. But now we're taking all this data, plugging it onto the axis below in the form of a box plot. Any questions whatsoever, folks, with prior parts before we get started? Oh, it is a dot plot. Thanks for mentioning that. You know, that's kind of weird. You know, after doing all of this, I would think we'd do a box plot. Oh, it's down below. Okay, so we are doing a box plot. I guess the idea is that this is a final exam review problem. I wouldn't ask both plots, but we're doing both just for the sake of reviewing. I think that was my thought. I just forgot. So first one is a dot plot, which means if you're doing a dot plot, you have to go to all of your original data way up here. I'll put this up as just a temporary screenshot and just put dots for every single value that comes up. It's kind of tedious, but it's not as tedious as a histogram. So there's that. So there's one at 20 years. Move over to 32 years. These don't have to be placed perfectly, but notice they float above the x-axis. We want the x-axis to kind of stand alone. The data is above it. So next is 34, 29, 30. 30 comes up twice, which means we're now stacking our dot on that value. 14 is way out here. 29 again. 11 way out here. We have a 38-year-old over here. Next, we're at 22, 44. Here's the outlier at 50 years. We ought to use a special color for that. So this one way out here was far enough away from the central data to be considered an outlier by the rule of thumb. Now skip to 26, 25, 22. That's a stacked 22 then. 32. I believe that one is at 32. 35 comes up. Now finally, last two, 19 and 25, stacking the value at 25. If you accidentally don't stack them, again, I'm not going to look at every single one of your dots and ensure they're perfectly placed. I'm looking for the big picture to see if anything just seems a little bit off. So as long as you've got something about like this, all your dots are in the right neighborhood, you get full credit for that kind of problem. We did it, folks. That's our dot plot. Next up is going to be the box plot. It looks like Part E wants us to comment on the box plot as well after we construct it. Any questions whatsoever before we go to the next plot? So for the next plot, when you're doing a box plot, what you want to look at is your 5-number summary and any information that you came up with about outliers. We did find an outlier 50 years, so let's put this on the axis. It plots as just a dot or an open circle, any kind of special symbol. Next value we can put down is, let's work on the quartiles. Q1 is at 22 years. So that's a horizontal line segment going up this way. 33 years for the upper quartile. Another horizontal line segment. The median is at 29 years. So we put that here as a central line in the box. At this stage, we can fill out the entire box like this. Kind of missed on the upper edge. Let me try again. So this line right here signifies now the median value at 29 years. So this already contains a lot of information. The central 50% of every observation age at that music site lies within this range from about 22 to about 33. But there's some values that trail off. They trail off to the minimum of 11 years. We plot this one in a kind of special way. At 11 years, we put a little segment that goes like this. This is called a whisker in the box and whisker plot, or just simply line segment. And it goes off like this, all the way to the green edge of the box plot. We try again on that. There we go. So now this tells us 25% of the data is in this extent, going this way. And last thing, the maximum was at 50 years. We don't go up to that one. That one is an outlier. We go up to the next smallest value that isn't an outlier. This is probably the trickiest part of the box plot. So let's take a look at the data again. Yeah, I think you're right. So 44 should be the oldest age below 50. Scanning through there, absolutely. We'll take the value at 44 years. Go up to about here. So here's the first data value, the largest one that wasn't considered an outlier. And that's the last whisker. So we got it, folks. That's the box and whisker plot if we ever have to produce them. And that's the dot plot if we ever have to produce that one. Here's the tough part now. We have to describe this box plot using the context of these data. Mention at least 3 items. So there's a lot of things you can say, a lot of different kinds of responses. As long as you're using the context, and what you say matches up with what's presented here, you're going to be totally fine on those 3 items. So if you don't know where to start, you could maybe begin by saying something about the outlier is always a good one. If it didn't exist, you could say there's no outliers. That's good information as well. Let's begin by saying there is an outlier. Of 50 years for the music site visitor. So our sample had that one outlier. We need to say 2 more things. Any volunteers for the other things we could say? Yeah, absolutely. It's not necessarily most because it's directly half of them, but it's really important to mention those because they're the center. That's where they're pretty much gathering from around here, either as a dot plot, as a box plot. So we could say the central 50% of all visitors are aged between, I forgot those values, looks like it's 22 and 34. At this point, you'd be reading them off the plot, so it wouldn't really have to be too perfect. Let's say 22 and 34 years. So now we have one more thing that we have to respond to, one more option we have to mention. kind of tough to think of these sometimes, but easy things you could say is maybe 25% of the observations go from 11 years to 22 years. Or you can mention this is 25% of the observations as well. Another thing you might even say might be, let's see, I forgot what I was going to say. Oh, you might mention skew. That's a fun one. If this line is directly in the middle, that's an indication that the data is pretty symmetric. But our median kind of moved closer to quartile 3. It means it's more spread out in this direction. Exactly. So we could say the ages are skewed left. And I think that'd be a great response. But again, you could say a lot of different things. Anything you mention here that's true as you see it on the plot is a good response. Some people might say the typical age, the median age is 32 years. Some stuff like that is great information as well. We mentioned the context anytime we said something like years in music site visitor. So all these things are context being mentioned. You don't have to say context on every single one of those, but if you never mentioned anything about what the original study was trying to do, then that's the point at which we did miss the context. Well, any last questions, folks, running through that data analysis? Okay, and by the way, now that we're pretty much through all the course and we have a bigger view of everything that goes on in it, this is called descriptive statistics, taking sample data and just describing what you see. Yeah. Oh, yeah, absolutely. So once you have your data imported, go over to calculate, hit enter, and you get to that screen right here. And then the last thing you have to do is just hit the down arrow button. And this gives you the 5-number summary at that step. Excuse me. That makes sense with that step? Awesome. Other questions at the moment? Okay. So some statistical problems are all about this. Just describe your sample and then we're done with it. But the hard statistical problems are these ones, where you use the sample data to turn completely around and start describing the population now with your sample data. That's what we were doing with the confidence intervals and hypothesis testing. But this is still good and very important stuff to statistics, so let's do another one. Let's say it says something about the technology committee at a college has stated that the average time spent by students per lab visit has increased. And the increased supports the need for increased lab fees. That seems like something they would typically say. We're upping the fees because more people use it. But they're having their feet held to the fire here. To substantiate this claim, the committee randomly samples 12 student lab visits, notes the amount of time spent for using the computer, and that's these times right here. So they're going to see if they really need to support that fee by just looking at some random data. I don't know how they randomly selected those 12 lab visits, but now that we have the data, looks like another one of those problems where we need the mean and the sample standard deviation. So let's go back to the calculator, hit stat key, enter, up arrow to highlight L1, and click on the clear button, enter again to wipe that out. Now we have 12 values to put in. Okay, I think I've got them all in. Yeah. No, not at all. That would be just fine. It could matter only if you're doing something like this one, where you have to make sure each of these data values correspond to the same entry. So that's the only time. Sorry, say again? Yeah, exactly. But for these problems, any order you put them in, totally fine. And I like how you mentioned that because sometimes when I'm putting these all in, I lose my place going left or right. It sometimes is easier to change the direction you import them. So that's a very good strategy. Yeah. It's easier sometimes if you have a paper because then you've got your finger to move along. Here, it's a lot tougher for sure. Other questions at the moment? Okay, so with all this data, hit the stat button, right arrow, and hit enter a whole bunch of times. This gives us the sample mean Y bar at, oh, I don't know why I'm putting it up here. Part A wants that information, so I should put it down here. You don't lose points for that, but it's just kind of weird to not put it in the right spot. So 62 point, we want 2 decimal places on this one, so 42. Again, if for some reason I just forgot to say the unit, do what to round to, just do what seems natural.
If we put X bar instead of Y bar, okay.
Totally okay, yeah. That's very tempting because our calculator supports it as well. So 62.42, and this is it's not years anymore. This is minutes spent in the computer lab. So about an hour on average. Next, the sample's standard deviation is 15.26 minutes. Now it looks like we're back to calculating z-scores. And you know, the bigger reason we did z-scores was these are test statistics. We were just getting used to the idea of measuring standard deviations, but they do have their own purpose as well. So we'll take z. A z-score formula would be y minus y bar. When we do our test statistic, you'll notice we always put either mu or p right here where we put y bar. Then we divided by a standard error, which was approximate standard deviation, or we did divide by a standard deviation for categorical. Here we just put the sample standard deviation S. So the trickiest thing is, what is y in this problem? Has anyone spotted it? Yeah, it would be the 8 minutes. Good call. So the 8 minutes right here is the y in the problem that we plug in. So 8 in this location, subtract 62.42. Divide this whole thing by 15.26. So we're comparing how many standard deviations 8 is away from 62.42. This will come out as negative, so we'll have a number of standard deviations below the mean. So the calculator can hit the parenthesis, 8 minus 62.42, hit the close parenthesis, and then go down to divide by 15.26. So that gives our standard deviation, and didn't say what to round to, so we'll just do what seems natural. Let's go for 2 places, negative 3.57. And 3.5 standard deviations is really far away from the sample mean. And that seems about right because 8 minutes seems pretty far away from 62 minutes in terms of those 15-minute standard deviations. So next question is now about solving an actual equation. On a final exam, this is usually the trickier question. We want to know what minutes corresponds to a z-score of 2.58. But first, before we do that, I should ask any questions on part B. Okay, so this one again is unusual. They provided the z-score. Z is 2.58. I'm not sure why I did that, but let me come down here and just rewrite this equation. If z equals 2.58, the strategy for solving this equation is make a huge substitution for z right here. So we take all of this, plug it into that location. So y minus y bar. Let's plug in the value for y bar as well. Y bar is the 62.42. We're dividing by S, which is the 15.26. And that's set equal to the 2.58. So all I've done in this step is carry down the z-score formula to this location, making a substitution, and then just plugged in y bar and S down below here. When it asks how many minutes, we're solving for the y right there. So once we have y solved for, we're in business. And here's what it would look like in a calculator. It's always the same kind of steps. Right in the right-hand side, 2.58. Immediately multiply by the denominator, 15.26. Visually, if you do these kinds of things visually, this is a cross product multiplying in that direction to clear out the denominator. So you have y minus 62.42 now equal to 39.3708. Last step is just to add the 62.42 to both sides. In the calculator, all you do is go plus, give it the value, 62.42. And now we have a value of 101. Let's round it to the nearest minute, 101.8 minutes. So y equals 101.8 minutes. So notice how this z-score here was a positive value. That means our answer, 101.8 minutes, had to be larger than the mean. And this one was a negative value, so that means the observation y, which was 8 minutes, had to be well below the mean. I feel like this is a good one to highlight as well. But that's the quick rundown on getting through the z-scores. Oh, thanks for spotting that, Tiffany. I put in a 2.58 and it should have been a 2.85. That's always a silly mistake. So 2.85 is right there. I should have noticed that. So let's make some corrections. It should be at 8.5. Then next correction down the line is 2.85 times denominator 15.26. I should have noticed that chat a little bit earlier. I would have catch that pretty sooner. Thanks for mentioning it, Tiffany. So 43.491 is what would have gone down here. Let me rewrite that one. And that one, giving us a 43.491. Then we take the 43.491 and add the 62.42 to it, plus 62.42, and we have 105.9 minutes. So that is a pretty big change, 105.9. Okay, any questions, folks, with getting through that correction? Algebra is kind of unforgiving with a mistake at the very first step. You have to track it all the way through, but it just meant we had to solve the equation twice the practice, I guess. Well, let's take a look at the next then. We're down to 8 minutes, so I think we could get a pretty good start on this problem. This one looks like it's a regression analysis style of a question. So the first thing we have to do is import 2 columns of data. X, we always plug into L1. Y, we always plug into L2. So when it says age and ears, this is the X data. For price, this is the Y data going that way. And the calculator hit stat key right away. Oh, hit enter right away. I'm not sure where I was going. Up arrow to hit clear and delete L1. Now we have to carefully put in these 10 values into L1 and then again for these values here. And I think the price is definitely the one to go slow on. Oh, I think I have a problem. Give me a moment. I'm double checking my work here. Okay, I have the duplicated value. but I have 315 twice. That would explain it. Okay, I think I fixed my error on my end. Anyone need any additional time? Let's take a couple more moments. Okay, so with the data imported, next step, hit your stat key. We go over to calculate, and we want an option down below on this list. So go down arrow until you see option 8. Linear regression is what this stands for, A plus BX. Hit enter on this. You should have L1, L2 here. Continue to hit enter if everything looks correct. And when part A says calculate the least squares regression line for these data, this is what we wanted. Let's put this down in stages. It's y equals A plus BX. So next step, plug in the value for A. A is 427,126. This is in money, so hundreds of dollars, hundreds of thousands of dollars. 47,2,126 point, because this is in money, I think rounding to the nearest cent makes sense. So 0.21 plus B, well, this is really a minus B, our slope is negative. So put in the B value next, it's 30,689. And 32 cents. So this is the least squares regression line. It's going to model Y. The price of, looks like we're dealing with Corvettes, and X, which I did forget there. Don't forget the X like I did. X is going to be the age of that Corvette in years. If we draw our regression line, probably something like this is what most people would do. That would give you full credit there. And now the slope is telling us a lot. It's the amount the Corvette will depreciate year after year. $30,000 is what the prediction is. But we'll have to come back to this problem to finish it off. Looks like it's this typical kinds of questions that you can expect there, where this is the technical calculator step, just getting the regression equation out. Well, any questions at all, folks, getting through to this stage? Okay, when we come back, we'll go to this problem number 3 right here, finish it off, and let's see what else is on this one. Looks like we have a probability question. We have a normal model question, and that's the end of those questions down below there. So we'll finish off 2.5 questions, move up to the top and do these. Not necessarily. I think this is pretty long for a real test, but it's a good representation of anything that can be on the test.
Okay.
Pretty much it's kind of my best attempt to take a document like this one, which is 54 pages, and condense it way down for a real class review. Well, any last questions at all, folks, before we call it a day? Okay, have a great night. We'll come back on Thursday and work through as many of these problems as possible. We may not finish them all, but anything we leave off, we will have solved and uploaded, so the total solutions will be available. Yeah, absolutely.
Thank you.
Yep, you bet. Take care.